Hi, we're going to talk about section 4.6, complex zeros, or the fundamental theorem of algebra. So far we found only real zeros of polynomials. But what about complex zeros? Are there any? Recall from the last video that we factored a polynomial to be x minus 1 times x minus 2 squared times x squared plus 4. We found that the real zeros were the set containing 1 and 2, but we can also see that if we take that last factor, this x squared plus 4, we can use it to find complex zeros. Why? Well, x squared plus 4 equals 0, which is the same thing as saying x squared equals a negative 4. And solving for x, we get plus or minus 2i, right? So f of x actually has 4 zeros. F of x has 4 zeros, right? They are 1, 2, 2i, and minus 2i, right? So once we know the zeros, we can write what's called the complete factorization. X minus 1 times x minus 2 squared times x minus 2i times x minus a negative 2i. Right here I'm using the factor theorem that tells us, if c is a zero of a polynomial, then x minus c is a factor, right? We're going to take a notice that f of x is of degree 5, right? We have 1x, 2 more x's, so that's 3, a 4th x, and a 5th x. If we multiply them together, we get the 5th degree. And we also notice that its 5th degree, it has 5, not necessarily distinct, but 5 linear factors. 1 linear factor, 2 more, that's 3, 4, and 5, both real and complex. Okay. All right, so now we can see, a polynomial can have real zeros. It can also have complex zeros. How do complex zeros affect the graph of a polynomial? It turns out that they don't, right? The coordinate plane is only the coordinate plane. It's a graph of real values. And since complex zeros are complex values, they don't show up. All right, well, if it doesn't affect the graph of the function, then why do we care about them? Well, the cool thing is that if we consider complex zeros as well as real zeros, any polynomial equation can be solved, and any polynomial equation can be written as a product of linear factors. Elliot, it's time for bed. Okay, I think Daddy's in the bathroom, so you might need to go in and ask him if you can go. Okay. All right. This idea that all equations can be solved or have solutions, real and complex, is called the fundamental theorem of algebra. The fundamental theorem of algebra says that every complex polynomial function, which we might call f of x, complex polynomials because the coefficients are all complex, of degree n greater than or equal to 1 has at least one complex zero. Right? So what that means that if you have that polynomial function set equal to 0, you can always find a solution. Right? Furthermore, if we take that polynomial function f of x and factor it into linear factors, we can also say that f of x has n linear factors and n zeros, of course by counting multiplicity. So every equation has at least one solution. Every polynomial equation has at least one solution in the real numbers. And, in the complex numbers. It could be real, it could be complex, but it's definitely complex. Alright, so how do we find zeros that aren't real, right? Well, after finding our real zeros, either through factoring or using the rational zeros theorem in conjunction with the factor theorem and the remainder theorem, any factors that have no real solution, we set them equal to 0 and we solve. We might have to use completing the square, we might be able to factor, or we probably will use the quadratic formula. Let's look at an example. We're going to find all complex zeros, find all complex zeros of f of x equals x cubed minus 1. Right? So you might already be thinking about what the real zeros of this function are. Think about this function. It's x cubed and it's shifted down 1. Right? So you're going to say, oh, it crosses the x-axis one time. Okay? Well, let's take a look at this. We know that it's the sum of cubes, the difference of cubes. So what that means is that it factors to x minus 1 times x squared plus x plus 1. Here I'm using the fact that a cubed minus b cubed equals a minus b times a squared plus ab plus b squared, where a is equal to x and b is equal to 1. Right? So that's something that you can recall from past factoring. Alright, so what this is telling me here, since x minus 1 is a factor, I know that 1 is a real zero. But what about here? Well, I can use the rational zeros theorem and say that the possible zeros, right, are of the form plus or minus 1 over plus or minus 1. So that leaves me with plus or minus 1. If I test those out, negative 1, does it go, is it a 0? I use all the coefficients are 1, 1, 1. Bring down the 1 times negative 1 is negative 1. Add those together, I get 0. 0 times negative 1 is 0. I don't get a 1. Okay, so I know that negative 1 is not a 0. Then I can also try positive 1, and it's actually going to turn out that positive 1 is also not a 0. Okay? So 1 and negative 1 are not zeros, which means I've found all the real zeros. So now I might be thinking about complex zeros. Well, it turns out that this polynomial here that I'm circling in green is a quadratic. So let's use the quadratic formula, right, to find the solutions of that quadratic equaling 0, and that will tell me the zeros. So if I set a quadratic equal to 0 and use the quadratic formula, I have to think about what my a, b, and c are. They're the coefficients of the three terms, 1, 1, and 1. And I know that x is equal to the opposite of b, so -1, plus or minus the square root of b squared, which is 1 squared, minus 4 times a, which is 1, times c, which is 1, all over 2a, 2 times 1. We end up getting -1 plus or minus the square root of 1 minus 4. Well, that's a -3 over 2, right? I can't take the square root of 3, but I can take the square root of -1, so I end up with -1 plus or minus I root 3 over 2, and I can split that into two different complex numbers. -1 over 2 plus root 3 over 2i, and -1 over 2 minus root 3 over 2i. Right? So my zeros then, the zeros of f of x equals x cubed minus 1 are 1, -1/2 plus square root of 3 over 2i, and -1/2 minus square root of 3 over 2i. All right? So I've done what I need to do. And I also want you to notice this. These two numbers, -1/2 plus root 3 over 2i and -1/2 minus root 3 over 2i, we call complex conjugates. So just as a reminder of what that means, you have a plus bi as a complex number, and then you also get a minus bi, right? Anytime that you find one complex number as a 0, you must also find its complex conjugate as a 0. And that is because, look at how it happened with the quadratic formula. We have this idea of plus or minus all the time, right? We're always going to be getting two answers. All right, so now we could write the full factorization of f of x as x minus 1 times x minus its 0 minus -1/2 plus root 3 over 2i, and x minus its other 0, -1/2 minus root 3 over 2i. And I know it's super pretty. We can get rid of a few of the parentheses, x plus 1/2 minus root 3 over 2i, but we can't get rid of all the different terms. We also get x plus 1/2 plus root 3 over 2i as the factorization. All right, let's take a look at this on Google just to make sure that these complex solutions that I have circled in blue here don't actually affect the graph. All right, so let's go back here. We're going to get rid of, we're going to get rid of all of this, and we're just going to graph f of x equals x cubed minus 1, and see what it looks like. Search, graph. Ah, look at that, right? Notice it has the 1, 0 here at 1, at 0, at -1. I'm sorry, at 1. Sorry, I'm trying to find it. Ooh, why don't we zoom way in? So we can really see that happen. Here it is at 1. Notice that's 0. And then it starts to be all negative here. It's kind of hard to tell. It might be easier actually by hand. Oh, you can see it's all underneath the x-axis until we get here.